Yo, what's up, guys? Welcome back, episode 93. It's gonna be a little bit shorter of a video. I'm gonna go to my buddy's place in about, roughly about an hour or so, probably even less than that. Probably have to start getting ready at 9. So yeah, this video is gonna be pretty much a little bit less than an hour. I've been away all day helping coach tennis and various things. So, but yeah, so. Yeah, I've got a crazy headache, man. Like, jeez, I still have it. And I go back like 3 hours ago, took a nap for 3 hours, like, just not feeling good. So it's gonna be a little bit of a shorter video. Really, honestly, did not want to record this video, but as we all know, the grind doesn't stop. We be going at it every day that I'm here. I just, I don't make any excuses to record a video. So, we're here fucking ready to run, do some problems. If that's one or maybe 2, 3, I don't know, but let's get straight into it. So let's check out our Pokemon of the day. Number 93, we got a Haunter. Let's check out the sound. Check out the evolution. Let's check out this beautiful evolution video. Hunter has had its cry changed through every Pokemon generation. Let's get the most recent. We can mimic it. That's our sound, man. Give one more. I sound like a dog. Nice. So yeah, we're gonna jump straight into check out maybe our problem of the day. See what we got today. Oh man, that blinds me every time, bro. Oh my god, dude. Jesus. Count good numbers. Let's take a look. We got a 49% acceptance rate. Must be a little bit tough of a problem. Digit string is good if the digits 0 index at even indices are even. Digits at odd indices are prime. 2, 3, 4, 5, or 7. For example, 2582 is good because the digits 2 and 8 at even positions are even, and the digits 5 and 2 are at odd positions are prime. However, 3, 2, 4, 5 is not good because 3 is at an even index, but it's not even. Okay, so the digits at even indices are even, and the digits at odd indices are prime. Okay. For example, 2582 is good because digits 2 and 8 are at even positions. 2 and 8 at even positions are even. Started index 0, 2, okay. And digit 5 and 2 at odd positions are prime. However, 3, 2, 4, 5, because 3 is at an even index, but is not even. Given an integer n, return the total number of good digit strings of length n. Given an integer n, return the total number of good digit strings of length n. Since the string may be large, return it modulo 10 to the 9 to the 7. Digit string is a string consisting of digits from 0 through 9 that may contain leading zeros. Oh, okay. So if we got n is equal to 4, we do 400 numbers. Okay. We do of length 50. Jeez, man, that's a long number. I think we're gonna need to optimize this somehow. I feel like recursion. Is recursion the best way to do this here? I don't know. Is there a formula we can use to find the count of all the good numbers? Coming across such math impression. Do this, please. Change int n to long n. I wasted 2 hours on this. To be completely honest, man, I have no idea where to start. There's some serious math. Think about this, and the only way I could think about doing this problem was doing the iterative version, but will the iterative version accept? I'm not too sure. And do I want to waste time doing the iterative version? Not really. That's what I'm scared about. You know, my intuition here is figuring out a way that we can check the length of every number, right? How we can loop through each number and find the length. Let's take a look, because I'm not. Oh man, my headache's coming back, bro. How to loop. Okay, wait, what is it? 1, 2, 2. Count good numbers. How to loop through each number and go up until the length of the number. It's too big. Good number, yeah, I understand. Bro, the crazy ass headache, dude. Oh my god, my head hurts. I in range 1 to n plus 1. Yeah, we're gonna skip this problem. I don't feel like I don't really like that problem. To be completely honest, I know I probably shouldn't be doing that, but I kind of. We only have a certain amount of time. I don't want to spend this whole video trying to figure out, something. Yesterday, I believe we finished on BFS. Let's look at validate binary search tree. We haven't done this problem 34% success rate. Jeez. Okay, let's do this one. This is a tough problem, but that's what I was thinking. Does BST have unique values? Why isn't BST unique? So in case we find the same value as the one we want to insert, we do nothing. Let's think back to this. So in order is in order, right? So we would go left, root, right, right? Post order, pre-order would be the normal way, root, left, right. And then post order would be right, left, root. Post order traversal, right, left, root, right? Visiting all nodes in specific order. First the left subtree, then the right subtree, then finally the root. Man, God, this shit is so hard to remember, dude. Like, root, left, right subtree. In order traversal is root, left, right, right? Just please, like. Left, then root, then right. Okay. Root, left, right. In order is left, right, root. What is post order? Okay. So let's do an in order traversal, right? We do this, we're going to do a recursive in order traversal, which would be left, root, right. Okay, so if we want to do so we want to pass in our node, right? To do that, we want to call out in order traversal, pass in our root, right? What do we want to do? Well, we want to check, okay, if node dot left and in order traversal node dot left, right? If not, then we want to do res.append node.left, right? Then we want to do, okay, if node.right, res.append if node.right in order traversal node.left. Let's return our, let's see what this gives us. Call it, right? And let's print our res. Input root 213. What do we got here? We got none, tree node val 1. Oh shit, we're inputting the wrong values, bro. My god, it should just be node. God, man, node.val. If not node, let's just return. Alright, this is our base case. See if this does any better. Okay. We're appending twice, so maybe we should get rid of one. Let's see what that does. One, two, one. What am I doing wrong here? Okay, so let's see. We start at 2. We call this, go to 1, right? Then we call this again, go to the empty node over here. Then we return, come back to this node, append 1, go right, come back to this node, see that it's null, come back. We don't append, right? Then we return to this one. We would append 2, right? Okay, yeah. Then call node.right. Yeah. Okay. So we're at this node, call node.right. Then we call node.left, return nothing. Okay. Come back. Append. Oh, shit. That's what we're missing. That's why. Okay. Okay, so we did in order. Now we need to check, well, is it increasing, right? So for I in range length res, if let's say if I is less than, so if res I is less than res I plus 1, we would just return false. Otherwise, we return true. But I think this has to go to -1, or else we're going to get the out of bounds exception. Why are we getting a... Why are we getting false? I in range length, I plus 1. Res I is less than I plus 1. Check 1, 2, 3, return true. Res I is less than. Bro, am I tripping balls, dude? Why are we flipping this around the other way? Bro, what? If res I is greater than or equal to res I plus 1. Is this run? Is this gonna submit? Wow. How does that have a 30% acceptance rate? It must be this trick, bro. The in-order traversal. I do want to make a note. In order to validate binary search tree, and then check if array is strictly increasing. It's a good one. Do some graph general, bro. Number of islands. Okay, not this one. This one's pretty easy. Surrounded regions, clone graph, then. What is clone graph? Did do this recently, April 3rd. About 9 days ago. How do we want to do this, right? Reference of a node in a connected, undirected graph. Return a deep copy. Clone of the graph. Oh, bro, this is such a weird problem. Yeah, no, I thought this was a very odd problem. Like, we'll do it anyway, but I can't remember what a deep copy is. A deep copy of a graph in Python means creating a completely new graph that replicates the structure and values of the original, but with all new nodes and connections, not just references to the original ones. Affecting the original. Okay. Can we print node.neighbors? Why the hell won't it print? Did I spell neighbors wrong? Okay. Let's solve it the BFS way. And then we can see if we want to solve it the other way. See how I'm feeling. Not feeling good right now. It's the same. q is equal to dq. Pass in our root, right? Root. Let's pass in. Okay. While q, right? We can pop from the queue, right? So let's do, well, node is equal to q dot pop left. Now we pop. Now we can manipulate the graph. So we could do, well, I feel like we have to create some sort of new node, right? Like head is equal to, what are we returning? A tree node. Head is equal to tree node. So we can do like curves equal to head or something, make that reference. We can do like this is where I'm confused. Next is equal to, let's do like tree node node.val. We can loop through the neighbors. For neighbor in neighbors, if neighbors is not none else, we get an array of neighbors. For neighbor in node.neighbors. I don't know if this is right. For neighbor in node.neighbors, then we can, well, we can do q.append. We probably need a visited array too, or else we're gonna keep going in fucking circles. All right. Totally forgot about that. All right, visited. Equal to set. Let's check. Well, if neighbor not in visited, all right, then we can add this q.append. Let's append our neighbor. And then we can add to our visited array. Visited.add neighbor. I believe we'd want to return our head.next. I don't think this looks right, bro. What the hell happened here? Brute is not defined. Node. Oh, bro, I'm so cheated. Oh my god. Tree node has no object neighbors. I don't know. 133 clone graph. Using tree node instead of node. Whoops. All right. Old to new. We create a hash map. Maps the current node to node.value. You have the tree node. We don't want a tree node. We don't want a head. We don't need a visited. But we need a hash map. Old to new. Which the node is the key. And then the node of val is the value. We loop through the queue. Changes the cur. You get rid of this. Oops, not all of it. Get rid of this. We did the BFS implementation correct. For neighbor. In this needs to be changed to cur. If neighbor not in old to new. Old to new. Neighbor is equal to node neighbor.val q.append neighbor. Connect current node's clone to the neighbor's clone. Old to new cur dot neighbors dot append. Bro, my head hurts so bad. Bro, what a weird ass problem, bro. Like, this is such a weird problem. Like, so we create a hash map here, right? Okay, with the value. Let's print out old to new. I want to see what it looks like. Where are these edges coming from, bro? Like, having an issue here. The microphone, bro. Just didn't check the microphone the whole video, so I feel bad if it's buzzing the whole video. Whoops. To be honest, I really didn't like this problem. I think this problem is stupid, to be honest. So we loop through all the nodes, right? Loop through the neighbors, encode our neighbors, right? If neighbor not an alt in U, we create the reference in the hash map and we assign it the value, right? We append the neighbor, and then we make the connection, right? So we do, okay, alt and U cur, then we reference the dot neighbors, right? And then we append alt and U neighbor. I don't really... What a stupid problem, like. Where are we actually making the deep copy? I feel like as a deep copy, you'd be making a new node. I think that's like what I think about deep copies. Like, I'm gonna set the washing, keep the washing going. 1 second. Alright guys, I'm actually going to call the video there. I just realized it's 9 p.m. I got to start getting ready. So appreciate you guys watching. We'll be back at it tomorrow with a longer video. So see you guys later.